Okay, so this is the shorter, I forget which multiple choice it is, but it's the one that starts with which of the following scenarios has a decrease in kinetic energy. Okay, actually, you need to write what I'm writing. It's pretty basic. So I just want to make sure everyone's on the same page with this stuff. So which of the following has a decreasing, so like going down kinetic energy. If you recall, kinetic energy is mass speed squared over 2. So it's directly proportional to speed. The answer probably has to do with that. A ball dropped from a bridge. Well, if it gets dropped, it's going fastest right before it hits the ground, so it can't be this one. Okay, a moon in circular orbit around a planet. I think that has constant speed. Kinetic energy stays the same, so probably not that one. A sphere launched up at an angle traveling upwards. That seems to have, what we need it to do. And an escalator with a positive constant velocity. Yeah, positive. It wants to know decreasing kinetic energy, so it's probably not the elevator. So I'm going to go with C. That's your correct answer. Because as the ball travels upwards, it slows down until it reaches its H max, its maximum height. So it's actually stops at H max. Okay, so on to the second one, a lab group. Anytime you see a lab question, think of your lab group and the pile of junk. It's usually useful. That's why we had it. Okay, so a lab group wishes to determine the work done on a cube of unknown mass by friction. So there's work and there's a frictional force along a straight path with a rough tabletop. If the lab group has access to a meter stick, so meters, measure distance or displacement, stopwatch to measure time, and a spring scale that looks like that would measure force, which of the following will provide the measurement needed to calculate work done by friction? Yeah, right here you might want to note that work equals force. It's also a change in energy, so keep that in mind. But let's say force of friction, and it's displacement, so dot S, and you're not going to need the dot, just the S. All right, so great. You're going to want to, on these, really read your answer choices because they all look the same. Okay, at an unknown, this is a lab question. It's good to know your input and your output. So, they just want to calculate the work done by friction. So, let's see what it says. At an unknown acceleration, so that would be like, I guess, an unknown force, use the spring scale to pull the cube while time is measured. Well, time's not really up here in anything that I wrote, so probably not that one. Okay, at an unknown constant speed, use the spring scale to pull the cube while time is measured. That one's not going to work because you don't have anything about force. They're not saying you're using the spring scale for anything other than just like a rope, so probably not that one. Okay, an unknown constant acceleration, use the spring scale to pull the cube at a measured distance. Again, I think it feels like the spring scale is just being used to pull something. At an unknown constant speed, use the spring scale to pull the cube a measured distance. Okay, I guess you could measure with the spring scale, so that doesn't really work. This one seems more realistic because this constant speed means that you don't have any acceleration. So your force isn't varying. It's going to be the same force the whole time. So yeah, because if you think about pulling something with a spring scale just at a steady rate, that's going to be how you get your readings. All these other ones I think would kind of mess those up. I guess not this one. But yeah, basically I see a good way to measure force right here if you actually think about doing this. And I see distance, which is what you want for work. So D is the correct answer. Okay, so an overly exuberant, and I forgot to write in freshman, is running down the hall in a disheveled state. Basically, I just added some extra words to make it weird. What forces enable the freshman to move forward? What I would do, take your fingers and just kind of walk across the table and see how that feels. What's pushing your fingers forward? Okay, this says a normal force exerted on the freshman by the ground. Well, there is a normal force, but I think that's more holding the freshman up. So if you look at this is a free body diagram of freshman foot. Weights pushing down. Okay. Normal force would probably be pushing whichever direction, depending on the placement of the foot would be like that. And then I am pretty sure that the force of friction would be somewhere in here. It's because, if it were slippery, the freshman would just slip. So I don't think it's this one. Because the normal force isn't really propelling it. I mean, it could be straight up. It just depends on his foot. Normal force exerted on the ground by the freshman. Well, we're not looking at what the ground's doing. It can't be that. So frictional force exerted on the freshman by the ground. This one seems like a maybe-ish. Okay, frictional force exerted on the ground by the freshman. Again, we don't care about that. We're looking at the freshman. So it is C. Okay, last one. A green ball and a yellow ball with identical diameters are released by a fourth grader at the top of a playground slide. Okay, so we've got a ramp. Kind of probably draw that. So got the two things falling down. Okay. They have identical, so the green ball takes more time to reach the ground. Balls are then taken to the second floor of a roof, which is flat, and kicked, so they have identical velocities. As the balls fall freely to the ground, which one lands first? So basically there's something going on, probably rotational inertia with the ball that took longer to get down there. But if they get launched off a building, they would be a projectile, meaning they're in free fall. Free fall means for either one of them, the only force acting on them is their weight. There's no outside force. And that therefore, I don't even have to worry about masses. The only acceleration on them is G. So since they're in free fall, it would be both of them together. Free fall. And just to prove my point, it might be a good idea for y'all to go ahead and write this. This would be either ball once it's been put in free fall. And if you notice your net force here, so that means these m's cancel out and your acceleration is actually acceleration due to gravity. So that's, kind of an explanation of free fall, and it's D.